Unit 6B, Lesson 1. In this lesson, we're going to start off by talking about the difference between theoretical and experimental probabilities. Then we're going to move on to discuss the difference between dependent and independent events. And then to finish this lesson, we're going to discuss some new terms that include the intersection, union, and complement of events. First, we need to discuss the difference between theoretical and experimental probability. Theoretical is referring to what we expect to happen based on mathematics. Experimental probability refers to what actually happens when you perform some experiment. Okay, so you can see some equations on the right. If we're taking the probability of some event, the theoretical equation tells us we're taking the number of favorable outcomes divided by the total number of possible outcomes. When we're talking about performing the probability based on some experiment, it's the number of times an event occurred divided by the total number of trials or events that you performed in your experiment. An example referring to flipping a coin, the theoretical probability, if you toss a coin up, whether it lands on heads or tails, it's going to be 1/2 or 50%. Let's say you perform some experiment, you toss a coin 10 times and recorded a head 3 times and a tail 7 times. So the probabilities based on your data, your experiment, the probability of getting a heads is 3/10. The probability of getting a tails is 7/10. If you would perform your experiment, say 100 times or 1,000 times, then your probabilities for heads and for tails is going to be closer to the theoretical values that we got based on the mathematics. Next, we're going to discuss the difference between independent and dependent events. Events are independent events if the occurrence of one does not impact or affect the probability of the other. Events are dependent events if the occurrence of one does impact or affect the probability of the other event. Now we're going to use a simple example to show the difference between independent and dependent events. There's only going to be one small change between these two events. So first, for the independent events. Suppose there is a bag with 6 red marbles, 8 blue marbles, and 4 green marbles. I select one marble from the bag at random and turns out to be a red one. I replace the marble and want to know the probability of selecting a red marble on the second draw. So if I'm looking for the probability of selecting a red marble, that is going to be equal to the number of favorable outcomes, which is going to be 6 red marbles, divided by the total number of marbles in the bag. So if I add 6 plus 8, I get 14. 14 plus 4 is 18. So 6 divided by 18, I could simplify to 1/3 or rewrite that as a decimal. So it'd be 0.33 repeating. Now we're going to take a look at the dependent events. There's only going to be one small change in this process. Suppose there is a bag with 6 red marbles, 8 blue marbles, and 4 green marbles. I select one marble from the bag at random. It turns out to be a red one. I don't replace the marble and want to know the probability of selecting a red marble on the second draw. So now when we calculate the probability of selecting a red marble, that's going to be equal to our number of favorable outcomes, which now, since we did not replace that red marble, is only going to be 5. There's 5 red marbles remaining. And now if we subtract 1 from our previous total, instead of 18, there's only going to be 17 total marbles left. Now if we write this approximation as a decimal, that would be approximately 0.29. So in the first event, when we replace the marble, there's a 33% chance that on the second draw, it's going to be a red marble. When we don't replace the marble, now on the second draw, there's only a 29% chance that it's going to be a red marble. So in the first case, independent events, the outcome of the first draw did not impact the outcome of the second draw because we replaced the marble. The second one was dependent because the outcome of the first impacted the outcome of the second because we did not replace the marble. To end this lesson, now we're going to talk about unions, intersections, and complements of events. So we have the term, and then we have a symbol that we're going to use to represent that term, and then how it's actually read when we discuss that term. So for a union, the symbol we use looks like a U, so it's easy to remember. That's read as OR. So whenever we have the union or the union symbol, that means OR. The second term is intersection, which we use an upside down U to represent the intersection, and that means and. And then the last term is the complement, which we use a bar above the letter. So if we have event A, the complement of event A, we denote with the bar across the top, and that includes all outcomes that are not in event A. Lots of times when we're using unions and intersections, complements to compare two events, we can use a Venn diagram to support that data. So we have one event over here represented by this circle. We have our second event over here. And then where those two events overlap, if they overlap at all, we're going to include that overlap in the middle. To end this lesson, we're going to go through an example relating the ideas of unions, intersections, and complements of events. We're also going to use a Venn diagram to help us out throughout this process. Suppose a class has 20 students. 4 students are wearing red shirts, 10 students are wearing blue jeans, and 2 students are wearing both a red shirt and blue jeans. Find the following probabilities if a student was selected at random. So first, we want to find the probability that a student has on a red shirt. So we have to take our total number of favorable outcomes, which is going to be 4, divided by our total number of outcomes, which is going to be 20 students. So we have 4 divided by 20. We could simplify that down to 1 over 5, or write that as a decimal, 0.2. So there would be a 20% chance that if you randomly select a student, that they're going to have on a red shirt. Now we want to find the probability of R intersection with B. So this means we want to find the probability of selecting a student that has on a red shirt and blue jeans. So we were told in our problem 2 students are wearing both a red shirt and blue jeans. So our total number of favorable outcomes is 2, divided by our total number of outcomes is 20, which we simplified to 1 over 10, which if we wrote as a decimal would be 0.1 or 0.10. So there would be a 10% chance that if we randomly picked a student, they would have on a red shirt and blue jeans. And remember, intersection means and. It has to satisfy both conditions. Next, we want to find the probability of randomly selecting a student that has on a red shirt or blue jeans. This probability is going to be a little more difficult to calculate. Okay, so now we're going to use the Venn diagram. In the middle, we have 2 in the intersection because we were told there's 2 students that are wearing both a red shirt and blue jeans. So you know in the middle, that overlap has to have a value of 2 students. Now if I just focus on the circle on the left, which represents the students wearing a red shirt, I know there's 2 in the middle already accounted for. So if there's a total of 4 students wearing red shirts, that means I need to have this 2 over here. So this means there's 2 students wearing red shirts that are not wearing blue jeans. We can use a similar idea on the right. If we're looking at the students that are wearing blue jeans, looking at this circle, we have the 2 students in the middle that are wearing a red shirt and blue jeans. So that means there must be 8 students that are wearing blue jeans but not a red shirt. So that's where these values come from. Now, if I want to calculate this probability that I select a student that is wearing a red shirt or blue jeans, I just have to add up all of these values. So I'm taking 2 plus 2, which is 4, 4 plus 8 to get 12 favorable outcomes, divided by the total, which is 20. We could simplify that to 6 over 10, which we could simplify again to 3 over 5, which as a decimal would be 0.60. So if I randomly selected a student, there would be a 60% chance that that student has on a red shirt or blue jeans. That student could be wearing both a red shirt and blue jeans. They just have to have on one of the two or both. Now we want to find the probability of R complement. So all outcomes that aren't an R. So in this case, all students that aren't wearing a red shirt. So if we know there's 4 students wearing a red shirt and there's 20 total students, that means there must be 16 students that aren't wearing a red shirt divided by 20 total students. We could take a 4 out of each of these, which would simplify to 4 over 5, or as a decimal, that would be 0.80. So if we randomly selected a student, there would be an 80% chance that they aren't wearing a red shirt. That's a complement of event R. Quickly summarize this lesson. In the beginning, we talked about the difference between experimental and theoretical probabilities. Then we moved on to discuss the difference between dependent and independent events. And then we finished this lesson by talking about the union, intersection, and complements of events and found some of those probabilities.